All right, so we're going to take some notes on polygons. Polygon means many-angled. Poly comes from a Greek word that means much, or many. Gon comes from a Greek word that means cornered or angled. All right, so polygon is a figure in a plane that meets the following conditions. It must meet all of these criteria. If it breaks any of them, it's not a polygon. So the first one is that it is a closed figure formed by 3 or more coplanar segments called sides. Sides that have common endpoints are non-collinear. In other words, if I have a polygon like this is a side. And then I draw another side, and these points are collinear. I could not call this a pentagon. Okay? So their common endpoints here cannot be on the same line. Each side intersects exactly 2 other sides, but only at their endpoints. So this means if I have something like this, this is not a quadrilateral because these sides intersect at a point other than the endpoints. All right, so again, it must meet all the criteria to be called a polygon. Now there's 2 types of polygons that we're going to look at. The first is a convex polygon, and here we have 3 definitions. Any one of them will do. You don't have to meet all of them. If you've met one of these 3 definitions, you have met all of them. Okay? So, no line containing a side of the polygon contains a point in the interior of the polygon. What does that mean? Well, here we have a polygon. If this is convex, then this line, that contains that side, has no points on the interior. This line that contains the side has no points on the interior, and so on and so forth. If that is true of all the lines, then this is convex. And it is, so this is a convex polygon. No diagonal contains a point in the exterior. This is an equivalent definition. So if I had some polygon like this, and I drew a diagonal connects 2 vertices. There are no points on this diagonal in the exterior. Diagonals are segments, and their endpoints are vertices. Okay? So again, this is convex because there exists no diagonal that has points in the exterior. The third definition is no interior angle measures more than 180 degrees. Less than 180, less than 180, less than 180, less than 180, less than 180. And these arcs are not meaning congruent. They're just indicating that I'm talking about these angles. Okay, so there's your 3 definitions that are equivalent for convex. The next one, concave polygon. A line containing a side of the polygon has a point on the interior of the polygon. So, let's say I have that polygon. Here's a line that contains a side. It has no points on the interior. But if there's even one line that contains a side that has points on the interior, then this is concave. Okay? The second equivalent definition, there is a diagonal that contains a point in the exterior. So, again, if I draw some kind of polygon and I draw this diagonal, It has no points in the exterior. But there does exist a diagonal, this one. As a matter of fact, all of its points are in the exterior. There's another diagonal here, which would have some points in the exterior and some in the interior. So if there is a diagonal that has points in the exterior, then it is concave. And the final definition is, there exists an interior point that measures more than 180 degrees. And there it is. Doesn't mean that there have to be more than one. It only takes one angle that has an interior measure of more than 180. It only takes one diagonal that has points in the exterior. It only takes one line that contains a side that has points in the interior. Okay, good. Regular polygon, we've done this before. It is convex. It's a polygon with all sides congruent and all angles congruent. All right, and then there's some homework here on page 61. There's very quick little problems in the book that talk about the definition. You'll just have to tell me whether they're concave, convex, and on page 2 of the packet. All right, but don't do them yet because I forgot something here. The other thing you have to do on page 61 here is you have to classify them by the number of sides. So you have this table. There we go. You have this table on the next in your packet, and I want you to fill in the names here of the polygons based on the number of sides they have. All right, so there's a chart here and a chart here. I added one as well. I'd also like to know the name of a 20-sided figure. So when you're looking up things like the 7-sided, the 9-sided, also look up the 20-sided for me. Okay. And one other quick thing. I want you to think about this investigation. Now, what we want to do is we want to come up with a formula. And the formula will tell me the sum of the interior angles. And I will only input into this formula the number of sides. Now I'm going to do some work here, and you're going to wonder why, but we're looking for a pattern, not necessarily answers. So the more you can write what you're doing, the better off you'll be in recognizing the pattern. Okay? So here we have a polygon, and it has 3 sides. Now, how many triangles can I create with this polygon? And what I mean by that is if I draw diagonals, how many triangles can I break this shape up into? Well, a triangle has no diagonals, so I can't break it up into any more than one triangle. And what is the sum of the interior angles? Well, one triangle, 180 degrees, so the sum of the interior angles is 180 degrees. Okay, the next one, again, has 4 sides. I want to break this up into triangles by drawing diagonals. Here we go. But I do not want the diagonals to intersect. I want all the diagonals from one vertex. I only can draw one diagonal. How many triangles do I have? I have 2. And each triangle has 180 degrees. So this answer is 360. And you already knew that. And let me just convince you that it's correct. This triangle, again, I'm just indicating not congruence, but I'm just indicating angles. That's 180. This triangle, 180. And you can see that I've taken care of all of the possible angles in the quadrilateral. All right, I just want to show you something before I go on to the next one. Let's say I have a polygon, oh, I don't know, something like that. All right, so these are the vertices. When I draw my diagonals, I want to pick a vertex, any vertex. I'll pick this one. And I want to draw all the diagonals I can. Well, I can't draw a diagonal to the adjacent vertices, but I can draw one here, 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 and I can draw one here. Notice I always went back to the same point. That way they don't overlap and I haven't missed any. And then I can count up the triangles and I can figure out the angles. Okay? So here, I'm going to pick a vertex. I'll pick this one. I draw all the diagonals I can from that vertex. Do not go to another vertex. I can't go to the two adjacent ones, but I can go here and I can go here. Okay. How many sides does this shape have? 5. How many triangles? 3. Each triangle has 180 degrees, and that's 540 degrees. I want you to complete the next two. Just be careful. This is a hexagon, and then it's an octagon. I skipped the 7-sided figure. Okay, so you're not going to get the same they're not going to be sequential right here. So your job is to come up with a formula so that I'm going to write sum of interior angles equals, and then you're going to write blah, 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 blah. It's going to have an n in it, the number of sides, and out of the formula will come the sum of the interior angles. Okay? It's not a hard formula. It's just that you haven't written a lot of formulas like this. So look at the patterns in the table above and see if you can get this number to come out by putting this number 5 into your formula. Okay. I think that's everything. So you're going to come up with that formula and you're going to fill in this table with the appropriate names. And finally, you're going to do these pages, which are quite easy, in the textbook, page 61 in the textbook, and then page 2 in the packet. There's a couple of little tricky drawings here. Don't be too concerned. Be a little creative here with the drawings. I'm just going to name things and you're going to draw an example of it. Okay, that's it.